Welcome back. Today we're going to start chapter 4 and look at trigonometry. Now you may notice two words or parts inside of trigonometry, and the TRI representing triangles and metry, which is the measurement. So we're considering the measurement of triangles. And the scope of trigonometry goes well beyond triangles, and many civilizations have used it, including Babylonians, the Polynesians, Mayans, and Egyptians. But it's really credited to the Greek civilization because they were the civilization that created something that we can read and follow, and sort of an ordered science, and a textbook description and explanation of trigonometry. And it was developed primarily with the Greek civilizations. And I put a couple of the Greek astronomers and mathematicians down here. Some of the key letters that we'll use for trigonometry come from the Greek alphabet, and primarily I would say alpha, beta, and theta. And you can see some other letters we often use: mu, lambda, sigma, pi. Okay. Oftentimes so far we've talked about these Greek letters as well. Okay, so when we consider trigonometry, we're going to have to look at the angles. Right? So triangles, we're looking at angles, and we're trying to standardize these angles. And so we want to make sure we look at angles in standard position, and that has two parts. We need to have the initial side, which lines up with the positive values of the x-axis, and then the terminal side. Now, the rotation tells us if it'll be positive or negative. So an angle that rotates counterclockwise is positive, and an angle that rotates clockwise would be negative. So when we draw and sketch these angles, we want to make sure we show that rotation. So this would be a positive, and then clockwise would be the negative. Now, when we look at an angle, we can also look at the reference angle. And the reference angle is always an acute positive angle that lines up with the x-axis. So we'll often try to figure out how to simplify this so we could see what's happening. What's that angle? Because you could have many revolutions, but eventually it will land in a quadrant or on a quadrantal on an axis. So for these two, we're actually going to first sketch the angles. All right, so if we have 400, we know that's going to be a counterclockwise rotation. And we want to make sure we line that initial side with the positive x-axis. And to do one revolution, well, that's 360. Well, we still have 40 degrees left, so that's going to take us into the first quadrant. And that's going to be a revolution, one full revolution, and then a little bit extra that takes us into the next quadrant. So we know this will be quadrant 1. We know that this acute angle, this alpha, would be 40 degrees because one full revolution would be minus 360, so that's 40. So that's going to tell us one of the coterminal angles. So anytime we subtract 360 or add 360, we're going to get a coterminal angle. So that'll still land in the same spot. Well, we could keep subtracting 360 to also get a negative, which would be negative 320. So if we went clockwise, we would land in the same position if we rotated it negative 320 degrees. Now let's look at 720. So 720, that's going to be a negative rotation. And I'm going to make sure I put this initial side here. Well, I rotate around once, that's negative 360. I rotate it around again, that's going to be negative 720, and we'll still have a little bit left over. So that's going to take us into the fourth quadrant. And that reference angle, I'll just put as 20, right? So that angle right here with the x-axis is 20. But we want to make sure we identify the quadrant. So that's going to be in quadrant 4. This will also have, we can give a lot of coterminal angles, but if I add 360, I'll get some, I'll get other coterminal angles. So I need to make sure I add 360, because if I subtract 360, I'll just keep getting negative values. So when we add that, we get negative 380. Well, if I add 360, I still get another negative, right? So that'll make me get down to negative 20. So negative 20 plus 360, well, that's going to be 340. All right, so we have two coterminal angles, and obviously there are a lot more, but we wanted to try to make sure we had a positive and a negative. All right, so let's look at some applications of degrees. And degrees are really important, especially when we talk about longitude, latitude, and location. So when we're searching for lost treasure or ships in the ocean, we'll often give the coordinates. So in any city, major points, even with your Google Maps, it'll give you your coordinates. So oftentimes coordinates are given in decimals. So if we have Montreal and we have Milan, here we have Montreal has a longitude of 73.567, and Milan west, that'd be west of Greenwich, and we have Milan is 9.19 degrees east of Greenwich. So even though they're decimals, we can actually break them down into different units, and we use degrees, minutes, and seconds, and that's based off of a regular clock, a circle. So if we have 1 degree here, and I'm just going to make a little drawing over here. So say, and this is not to scale by any means, but if this represents a degree, well, we can divide that degree into minutes, and there'd be 60 minutes in a degree. We could further divide each minute into seconds. There's 60 seconds in a minute, and we're using that same analogy with time to figure out the coordinates in degrees, minutes, and seconds. So for these two problems, we're actually going to convert the decimal into degrees, minutes, and seconds. So you can already see we have some of our answers right here. We have 73 degrees. That doesn't change. And what we're going to do is take this decimal, and we know that it's 60 minutes in 1 degree, so we're going to multiply that by 60 to give us the minutes. So that'll be 34.02. I did write that down. So we'll have 34 minutes. And now we're going to take that leftover, that residual right there, and that's going to help us figure out the seconds. And remember, there's 60 seconds in a minute, so we're going to multiply that by 60, and that equals 1.2. So this will be 1.2 seconds. So this is just another way to write coordinates. We can have the decimal coordinates, and I could make sure I write down west. So we have the decimal coordinates, and then we have the degrees, minutes, and seconds. Now let's look at Milan. So we have 9 degrees, and we're going to convert 0.19, which is this decimal, into minutes, multiply that by 60. So that equals 5.4. So that's going to be 5 minutes. And then I'm going to take the decimal 0.4 and multiply that by 60, and we get 24 seconds. So Milan is east of Greenwich, 9 degrees, 5 minutes, and 24 seconds. Now let's calculate the distance between the two cities. And we can actually do this pretty easily because they have the same latitude, about, for this problem I rounded, but 45.5 degrees north. So we're just looking at this distance. So if we have, I'll just put two cities here. We'll have, can't really see it, but Montreal's over here, right? It's kind of off the map here. And then we have, I'm gonna put it down here. So then we have Milan's over here. You can't really see it very well, but this map's probably not the best, but we're saying it's on the same degree of latitude, which is 45 is about here. And these two cities, we're just finding the distance between those two cities. So what we really need to do is find that central angle. So if we find that central angle, we know that Montreal is 73.567 degrees west, and Milan is 9.19. So if we have these two angles here, right? So Montreal and Milan, we can find the central angle. And remember, this is in relation to Greenwich, to New England. So if I add those two angles, that's 9.19. I'll get the whole central angle. So when I add them, I get 82.757. And remember, this is out of a whole circle. So that's going to be a fraction of the circumference. And we're given that the radius is approximately 4,000. So the circumference is approximately 8,000 pi. So we can find that distance, or that arc length, we're going to talk about that a little bit more, by cross multiplying. So the distance here is about 5,777, and we'll put point around at 53 miles. Now let's consider radians. So radians is another way of measuring angles. And what we're looking at is the arc length, S, and the radius. So if we remember, looking at any circle, if this has a radius of 1, we know that this whole circle would have a circumference of 2 pi. So 2 pi radians represents a full revolution. Now, if I was going to cut that in half, well, that would just be pi. And if we divide that by 2 again, or 1/4 of a revolution, that would be pi over 2. And if we divide that by 6, well, 2 pi divided by 6 is pi over 3 radians. Now let's look at some of these revolutions here. So again, we said a full revolution, a full cycle around, is 2 pi radians. Half is pi, a quarter is pi over 2, an eighth would be pi over 4, and then we can continue to divide them to get those fractional pieces. So what we're going to do is, for each of these angles, we're going to sketch them, find the quadrant, give two coterminal angles, and see if we could find any complement or supplementary angles. So looking at 9 pi over 4, well, we know that if this is pi over 4, we know that 8 pi would give us a full revolution. So that would be 8 pi, and then 9 pi would take us into quadrant 1. So this is going to be first quadrant angle. This reference angle would be pi over 4, right? Because 8 pi over 4 gave us 2 pi, which was the full revolution. Now, if we want to find the coterminal angles, well, I already found one. So finding those coterminal angles, 9 pi over 4 minus 2 pi, right? So I'll just rewrite that as minus 8 pi over 4. So we know pi over 4 is a coterminal angle. And then what we can do is subtract 8 pi over 4 again to get one of the negatives. So pi over 4 minus 8 pi over 4 would be negative 7 pi over 4. So we have a positive and negative coterminal angle. Now this angle, this rotation, was bigger than 360, or whole rotation, 2 pi. So remember, when we have a complementary supplementary angles, we need to have an angle that's an acute angle to have, so it can have a complement or add up to pi over 2, or we need an angle that is less than pi to have a supplement. So this rotation would not have a complement or supplement. Now let's look at 5 pi over 12. Well, 5 pi over 12 takes us into the first quadrant. And this is also going to be the reference angle. It's an acute angle. So we can tell right away this is an acute angle. It's going to have a complement. It's going to have a supplement. It's in the first quadrant. So what I'm going to do first is actually find the coterminal angles. Let's do that. So to find the coterminal angles, we can add 2 pi and subtract 2 pi. And remember, 2 pi, if I make that with common denominators, would be 24 pi over 12. So 29 pi over 12 would be a positive. And then if I subtract 24 pi over 12, we'll have negative 19 pi over 12. Okay, so we have a positive and negative right here for coterminal angles. Now let's find the complement and the supplement. So the complement, well, we know that if this was a full rotation, this would be pi, and we know that this 90 degree would be pi over 2. So pi over 2 minus 5 pi over 12, and I could rewrite that as 6 pi over 12. Well, the complement would just be a pi over 12. And the supplement would be just pi minus, oh, I didn't mean to erase that, all of it. So pi minus 5 pi over 12. So this will be 12 pi over 12. So we know that 7 pi over 12 would be the supplement. So again, looking at these two pictures here, this piece right here has to be pi over 12. And then I'll use a different color. So this angle, which I already had in pink too, that's going to be the 7 pi over 12. And remember, when we add them together, they should equal pi to be supplementary, and they should add together to be equal to pi over 2, so that they can be complements. All right, so you probably started to see ways that we're changing from radians to degrees. And the key idea is that we know that 2 pi radians equals 360. Right, so those two, that's a full revolution. So if 360 is 2 pi, then pi is going to be equal to 180, which we talked about with the supplementary angles. So when we're changing and converting from values, we're going to either multiply by pi over 180 or 180 over pi. So if we're converting 135, well, we want to change that into radians, so multiply that by pi over 180. And I'll write this out, but we know that these two numbers can reduce. They can be divided by 45. So this reduces to 3 pi over 4. And you could put radians. I'm going to assume that it is radians, otherwise just make sure you write the degrees. So negative pi over 6, changing that into degrees, we'll multiply that by 180 over pi, or the pi's will cancel out, and we'll have this equal to negative 30 degrees. All right, now let's consider a few ways that we can use radians. And the key idea is, we actually used it before when we were looking at cities, the distance between Milan and Montreal. But when we look at the arc length, which is going to be the length around the circumference, that's going to be a fraction of 360. Another way to write it is to say, well, we can multiply the radius times theta, which is going to be in radians. So remember, we know that if the angle was in degrees, it'd be divided by 360, and then we'd have to find that fraction of 360. So when we have an intercepted central angle with 240, what we want to do is make sure we simplify this, or rewrite it, I should say, with radians. So 240 and 180, well, 60 can go into both of them, so this will be 4 pi over 3. And then if we want to find the arc length, it's just going to be r times theta, and we know that the radius here is 4. So 4 times 4 pi over 3 would be 16 pi over 3, and that's going to be in inches. All right, for the next one, we have a radius of 27, And the angle is 160. So when we multiply that by 1 pi over 180, well, that can reduce to 8 pi over 9. So we know the arc length will just be 27 times 8 pi over 9. And that can cancel out. So the arc length would be 24 pi inches. Now let's look at the area of a sector. It's the same idea. It's looking at a fraction of 360. But when we use radians, it's a little bit faster. So the area, remember, is pi r squared, right? Is going to be the area of the whole circle. And then if we looked at pi, well, pi is actually half of a full revolution. So what we can do is change the 120 into radians. So 120, multiply that by pi over 180. And that's going to be, well, 60 goes into both of them, so 2 pi over 3. And then we know that since the area equals 1/2 times the radius squared times theta, well, this can reduce, and we'll get 4,900 pi over 3 feet squared, or I can actually just find the decimal. Let's see. So that's going to be 5,131.27 feet squared. I'll just include both since it didn't say to round. Okay, now the last thing we want to make sure we look at is linear and angular speed. So this is really saying if there was a little fly that was, or a Ferris wheel or some sort of object on the circle, or even you on a planet, right? You're rotating at a speed depending on the revolution or the speed of whatever is something is on, the object's on. So if that's a carousel, it might be something on the ball, like the logo you on a planet, right? So when we're finding the linear speed, we have to find the arc length. Okay, the arc length is really that circumference, and it's going to be the speed, so the arc length over time. So when we look at linear speed, we're going to find the linear speed of a clock, right? The tip of a second hand. And we said in this problem, it has a radius of 8 centimeters. So remember, for arc length, that's just going to be the radius times theta. And we know this is going to be 8 times 2 pi. That's a full revolution, right? So 16 pi is the whole circumference. And a clock is going around, the second hand's going around every minute. So it's going to be 16 pi centimeters per minute. Okay, so it's going to keep clicking around and it'll make a full revolution after 1 minute. Now let's look at the angular speed. So the angular speed, well, we can often, if we have the angle, or if we can end the time, we can find the angular speed. So for this one, we're actually going to use, we're already given the angular speed. So here we have 2,400 revolutions per minute. I should say the rotation speed. We want to find the angular speed that has radians, in case it has to have a measurement for angles. So just a brief distinction for the linear speed, it has a linear distance. But the angular speed is going to have an angular distance, or an angle measurement, I should say. All right, so for this angular speed, we have omega is going to be 2,400 revolutions per minute. And what we're going to do is change that to radians per second. So we know 1 revolution is equal to 2 pi radians. And then we also know that 1 minute equals 60 seconds. So we can simplify this. The 2's cancel out. We're going to reduce that to 2,460. That's going to be 40. So we have 80 radians I don't want to forget the pi. So 80 pi radians per second. Now, knowing the 80 pi radians per second, I can actually find the linear speed if we're given a radius. So if we know that the radius was 4 pi, well, if I write this out, so the linear speed, I'm going to have 80 pi radians per second. And you can go back and use the formula too, but this might be a little bit easier. You know that 2 pi radians, well, that's a full revolution, right? Is going to equal the circumference, and the circumference would be 8 pi because the radius was 4 inches. Well, then we could just simplify this. That's 40, and we'll have 320 pi inches per second. All right, I hope this lesson was helpful, and I'll see you all in class.